Hello friends, welcome to CEC Gurukul live lectures. Dear friends, from today onwards we are going to talk in our newly created series on classical mechanics. This is the first lecture on classical mechanics, and I would say this is the introductory lecture where we are going to discuss in detail what classical mechanics is. Friends, for the discussion on the topic, we have with us in our studios Dr. Sonia Bansal. Dr. Sonia Bansal is Assistant Professor in YMCA University of Science and Technology. Friends, she is a prolific professor, and we are always delighted to have her in the CEC studios. If you wish to ask questions from Dr. Sonia Bansal on today's topic, then feel free to talk to us through our toll-free number. Our number is 1800110430. I repeat, our number is 1800110430. Now, I would like to welcome our guest, Dr. Sonia Bansal, and would request her to explain us in detail what classical mechanics is. Hello, ma'am. Welcome to the lecture.
Thank you, Geetika. Dear students, we are discussing today about the classical mechanics. Why we discuss about the classical mechanics? The perspective of classical mechanics is very essential to understand the quantum mechanics. So it is very important to know the phenomena behind the classical mechanics so that the quantum mechanics can be very clearly understood. The classical mechanics, where we are talking about the physics in between the era of 17th century to the 20th century. After 20th century, the quantum mechanics or the modern physics came to the account. But this classical mechanics is a very important part of the physics to explain the further part of quantum and the modern physics. Now, today we will discuss about the introductory about what are the classical mechanics and what are the formulas behind the classical mechanics and how we use in the systems or the particles movement or the body motion. So now we start with the classical mechanics part 1 lecture in this series. Then first we understand what is the mechanics. As we talk about the classical means classical old, and mechanics means where we discuss about the energy and forces that affect on the bodies. It means mechanics means motion. Motion changes the position of the particle. Now, what is the exact meaning of the mechanics? It is a branch of physical science that deals with the energy and the forces and their effect on the bodies. Mechanics concerned with the two parts. One is the motion and second is the cause of the motion. Motion of the object, which can be explained by the velocity and acceleration. But how this velocity and acceleration changes? By using the force and the energy. Means motion of the objects means velocity and acceleration we are calculating, and what is the cause of this motion is the force and the energy. The objects move but do not change their properties. It means motion takes place in a body or a system, but its property will not change in the classical mechanics. The idealized particles and the rigid body are the example of that. Mass and the moment of inertia are all what matters in this mechanics. Newton's three law of motion, we all know about it and is not required to explain here. Now, what are the difference between the classical and the modern physics? As I already told that classical physics is in between the era of 17th century to the 20th century. The modern physics means we are talking about the 20th century, where we discuss about the quantum mechanics and the relativity. But in the classical mechanics, it is a pre-quantum mechanics, which includes with the spatial theory of relativity as well as the electromagnetic theory. EM waves also defined in this. Why we require the classical mechanics? There are the three good reasons which explain that classical mechanics is important in the physics world. Means we discuss about the close connection to the modern physics. Like if we master in the classical mechanics, then we can get the clear view about the quantum mechanics. It is easy to understand the quantum mechanical phenomena if we know about the classical mechanics phenomena. It is a powerful and versatile mathematical tool, and it is indispensable for advanced studies in the physics. where we, in this classical mechanics, we reformulate the familiar laws of the physics using the completely different approaches. Like, means we are defining the general formalism, and it is very easy to understand the classical mechanics in terms of the mathematical treatments. Now, Newtonian mechanics. In principle, Newtonian mechanics of the motion, what it works, it predicted the motion of any object from the force. All we need a big or fast computer to understand it. In reality, life are not so easy. So more fundamentally, the force may not be known. It may depend upon the time, location, or even velocity. For example, greater than two objects attracting each other by the gravity, that we will define. Solving three body problems turns out to be impossible. If we talk about the real life problems, then these are the problems created. Then it is caused for the more powerful mathematics required to define the mechanics. Mechanics where we use the most of the mathematical formulation in the classical mechanics. Here we discuss about the generalizing equation of the motion. What are the generalizing equation of the motion? By which we will define the position of the particle or motion in the particle. By this equation we will define. Newtonian mechanics deals with the object's position. Here we see our goal is to find the position of the particle in a particular system in the x, y, z coordinate. Here we will define that x is equal to xt. It means at particular time we are getting the position of that particle in the x coordinate. Y means we are getting the y is equal to yt, and z is equal to zt. It means all the position with respect to the time will define here. It is a goal of the Newtonian mechanics, where we will define the object's position with respect to the time. The three coordinates for the each object will be defined by the 3n for the n object. If we are having the n object, for the one object we are defining the three coordinates, and if we are having the n objects, then we will define the coordinates 3 into n. But there are the infinite other ways to describe the motion. Like here we define one more way of natural, define the pendulum, motion of the pendulum, where we define the coordinates in terms of the angular value. Here x is equal to L cos theta, y is equal to minus L sin theta, z is equal to 0, and theta is equal to theta t. Number of free variables here may not be 3n. Let us call the new variables here, which is the generalized coordinate. What are the equation of the motion for the generalized coordinate? That we will discuss. Before that, we will understand what is the degree of freedom and what is the generalized coordinate. What is the system of the particle? If we consider a system, and here we consider a position of the particle, then we will define it by the three-dimensional coordinates. Then we need 3n number of independent variables to define the position of a system consisting n number of particles. That's why I define it as a 3n. Now, if we are having the k number of constraints or we are having the k number of the restrictions, then we have to define it by 3n minus k number of the independent variable. Before we define a 3n number of independent variable, if we add the constraint in it, then it will be the 3n minus k number of independent variables. We define that degree of freedom of the system as 3n minus k. It is known as the degree of the freedom for the system as a 3n minus k. By looking the system, we can define these independent variables, and they are called these are the independent variables. That's why they are called the generalized coordinate, and they are denoted by the q1, q2, and up to the qn. If we are having the n number, then we will define up to the qn. Constraints. What are the constraints? Here we use the word k number of the constraints, that is the restriction, or k number of the restrictions. What are the constraints? Constraints can be classified into two parts. First is the holonomic constraint, and second is the non-holonomic constraints. What are the holonomic constraints? Where we expressed as a function of the space coordinate and the time. That are the holonomic constraints. Example are the rigid body. If the length between any 2 points is a constant, so it is called a holonomic constraints. If we consider a fluid, here the length between the 2 points is constant. Consider a rigid body, that is the holonomic. If we consider a fluid inside the spherical vessel of the radius, then the distance between the center of vessels and the fluid particle, then it is defined it as r less than equal to a, then we will define it as a non-holonomic constraint. It means here the length is constant, here it is varying, it is maybe less than or greater than the value of the, here a is the distance between the center of the vessels and a fluid particle. That's why this is known as the non-holonomic constraints. Its degree of freedom of a system means the number of independent variable, where we define 3n minus k, that is the degree of freedom of a system, which defined by the number of independent variables required to define the system. A system can be defined by the independent variables, then it is known as a degree of freedom. After observing the system, so one can define the generalized coordinate. Here we having the example of the simple pendulum. Since the system has a one particle, need 3 independent variables in the x, y, z coordinates. Then constraints means particle move only in a plane. That's the constraint. Second, length of the string is the constant. Here we are using the 2 constants. Now therefore we can define it as 3 minus 2 is equal to 1. That is the independent variable. That is, if has a 1, it is has a, this is a 1, this is has a 1 degree of freedom. Like 3n minus k, here 3 is the coordinates, minus 2 is the constraint, then 3 minus 2 is equal to 1, 1 now is the independent variable in which the particle can move, then it has it 1 degree of the freedom. And it defined the generalized coordinate as an angle between the downward vertical and the string, that is the 1 degree of the freedom, the motion of the particle. The most important part in the classical mechanics is the Lagrangian formulation. To define this, we remember about the Newton's equation. As we know that Newton's equation for the force F is equal to ma. F is the force, m is the mass, and a is the acceleration. We can start it with the F. F is the force. Here we take it force is equal to F x t, means force in the x direction at a particular time t for all the particles. Now 3n function corresponding to the 3n coordinates, means we are having it n particles and defined by the 3 coordinates, then 3n functions corresponding to the 3, now it will become the 3n coordinates. Forget the force, now introduce something else apart from the force from the Newton's equation. We will define the Lagrangian. How we define Lagrangian? L is equal to L q comma q dot. Dot means which define the coordinate q and its time derivatives. Q define the q, already we defined that the generalized coordinate by define the q. Here this coordinate q and it define its time derivative. The q represent the coordinate q and its time derivative. So Lagrangian may be defined L is equal to L q into q dot. Now Lagrangian equation will become d by dt del L by del q dot minus del L by del q is equal to 0, which define that everything about the system is embodied in the scalar function, that is the L. Here L is the scalar function. Lagrangian does not depend on the coordinate system. Then switching a different set of the coordinate is a snap, means this force is changes with the Lagrangian function, and here it is defined by the Lagrangian equation defined by the d by dt del L by del q dot minus del L by del q is equal to 0. In brief we will discuss later. Second most important part in the classical mechanics is the Hamiltonian principle. Hamiltonian principle derives the Lagrangian equation for a simple rule. What it indicates that integral of L is stationary for the path taken by an actual physical system. Means here we define the integral here 1 to 2 is stationary path defined to define a system movement or particle movement in a particular direction. That's why here we write it as del 1 to 2 L dt is equal to 0. Newton's law were found by induction, which defined at it is so because it agrees with the many observations. Deriving them from a particle means knowing why it is so happened. Not quite too dramatic, but it suggests the deeper reason eventually connected by the Feynman path integral. Beside calculus of the variation is a useful technique to define the Hamiltonian principle. What is the Hamiltonian formula? Hamiltonian equation, we can define P and Q. Here we define the canonical variables. What are the canonical variables which define the position and the moment? P is the position, K is the momentum. Then H is called as a Hamiltonian. It is a function. H is a function and it is called a Hamiltonian function. Then Q dot we will define del H by del P. Both are dependent. Position and momentum are dependent. Q dot dq by dt is equal to del H by del P. It is the Hamiltonian function. And minus P dot, which is the P is the position, defined by del H by del Q. Canonical variables were defined the position and position and momentum we already know about. P is equal to mv, and these are not related. The position and moment are independent variables, like allows wider range of variable transformations than Lagrangian formula. This Lagrangian formulation is a very clean, systematic and cool. And here quantum mechanics does with the uncertainty principle. And what are the success out of the failure? There we define the three body problems which failed unless we cannot have the invention of the computer that time. That's why it was not explained. Byproduct, where we are using the Lagrangian and Hamiltonian, turn how to be the quantum mechanics. Development of the quantum mechanics were guided by the analogies to Lagrangian and the Hamiltonian formula. Then quantum mechanics group up with the classical mechanics. It means classical mechanics generate the quantum mechanics. The classical mechanics is the missing link between the neutrons and the Schrödinger that was explained by the quantum mechanics appreciately. Why we are studying this quantum mechanics, classical mechanics, as we are saying that most of the part it could not be explained, but it is very important physics part where we define the Lagrangian equation in Hamiltonian principle. In our further lecture, we will discuss about the Lagrangian equation and Hamiltonian principles, where we deals with the central force problem, rigid body motion, oscillation, extension of spatial relativity, and then we discuss about the Hamiltonian equation in which canonical transformation, where we define the Hamiltonian Jacobi equation, or some of the advanced methods we will discuss, that is the classical chaos, perturbation theory and the field theory. We start with the elementary principles behind the classical mechanics. First we discuss about the single particle. Particle, object with insignificant size is defined the particle. Electron in the CRT tube, for example, electrons in the CRT tube. What is a particle? Object with insignificant size, and examples are electron in CRT, baseball thrown by a pitcher, earth orbiting the sun. Those are the examples for a single particle. It is having a mass and having a location, mass defined by the m and location defined by the r. On the basis of that, we define the velocity. It will be v is equal to dr by dt, and this derivative we can write it with the r dot position, and we put the dot that define the derivative. Linear momentum, this is the velocity, and the linear momentum we will define p is equal to mv. Momentum defined by the m is the mass, v is the velocity. Velocity we can take it from here, that is r dot. Now we can write mv is equal to mr dot. Now Newton's second law of the motion will be F is equal to dp by dt, change in the momentum, which is equal to p, we can write it as p dot, and this p dot we can write it as mr double dot. Mass is the constant quantity, then the location will be changed, then it will be double derivative. That's why we can write it in F is equal to dp, dt is equal to p dot is equal to mr double dot. In near future, we will define the force by mr double dot, where m is the mass, r is the location or the position of the particles, and this is a double derivative. Now, inertial system. What is an inertial system? Inertial system where we start with a particular origin O of r is somewhat arbitrary. We take the origin and we choose the origin as a reference frame. So, inertial system where we define a reference frame in which F is equal to P dot holds. It means which obeys the Newton's second law. Newton's second law should be stated more precisely as we define it as there exists the reference frames in which the time derivative of a non-linear momentum equal to the force. Non-linear, this is the linear momentum, and which is equal to the force, that is defined the inertial system. And there are infinite number of such frames which define the origin or the reference frame, or is defined as an inertial frame or defined as an inertial system. Again I repeat that what are the inertial system where we take F is equal to P dot, which obeys the Newton's second law, which explain that there exist reference frames in which the time derivative of the linear momentum equal to the force. This time derivative of the linear momentum which is equal to the force. Here we see that this dp by dt is equal to p. Momentum with respect to the time is defined the force, and if it follows, then it obeys the second law, and it is the inertial system, and we are having an infinite of such type of a system. Inertial system, we consider the two inertial system here. One is the A and second is the B. Now a particle is at RA. Here the particle is at RA. Here we are having the two inertial system A and B. The particle is from here to here, that will be defined by the in A. A particle is at RA in the A, and the particle in RB is in the B. The origin of A is at here. We see that the origin of A is here, is the origin is here RB minus RA in B. That's why we are defining it as F is equal to MRA double dot is equal to, we are defining the force of that particle. MRA double dot is equal to MRB double dot, which is equal to RB minus RA is equal to 0, or we can write it as RB dot minus R dot A is equal to constant. Any two inertial system are moving relative to each other at a constant velocity. Here it means RB minus RA is equal to constant. Here we are having the double derivative, or we can write it as RB minus RA is equal to 0. Then if we take the derivation of that, it will become the RB dot minus RA dot is a double dot, here the single dot, double derivative, single derivative. In the single derivative it will be the constant. Then we define the inertial frames, system moving with related to each other with the constant velocity. Here we define the velocity, that it is moving with respect to the constant velocity. The equivalence of the such systems was pointed out by the Galileo, and it is known as the Galilean system, where the two inertial systems moving relative to the each other with the constant velocity. Now next is angular momentum, which is also a important parameter of the classical mechanics. How we define the angular momentum? We define the angular momentum by L is equal to R into P. L is the angular momentum, R is the position, P is the momentum. It is a cross product of the position and the momentum. Now the momentum of the force, or we can say torque, which is equal to N is equal to R into F. The order matters. Then now from the F is equal to P, we can deduce it as N is equal to L here, because here we are having the F is equal to P, then we can put the value of N here, then we are using it as N is equal to L dot. N is the force, moment of the force, or we can define it as a torque, which is equal to the angular momentum, differentiate of the angular momentum. Too easy to write down here. For the torque, N is equal to L dot. Now that definition depends upon the origin. What is the origin of that? Where we are defining the R is the position, and R is defined from the O, from the origin to the distance of that particle, we will define by the R. The equation N is equal to L dot holds for any origin. We can take any origin, and then we can define this torque as N is equal to L dot, which is the angular momentum of the particle. Momentum conservation. How we define the momentum conservation? Two conservation theorems follows that. From first, we are knowing that F is equal to P, force is equal to momentum. Then we define if the total force is 0. If the total force is 0, the linear momentum is conserved, because dp by dt is equal to, then P will be the constant. If F is equal to 0, then dp by dt is equal to 0, then P will be the constant. That's why we are writing it as here. The total force F is 0, then the linear momentum P is conserved. Now N is equal to torque is equal to angular momentum, N is equal to L dot. If we take torque is equal to 0, then angular momentum L will be the conserved, and it is very easy to understand that the conservation of the here the P is also conserved, here the angular momentum, linear momentum and angular momentum both are conserved in this system. Why? The work by the external force. If the external force is applied, then what happened? Then particles move from the point 1 to 2 here in this diagram under the force F. Now the work done from 1 to 2 by the force F is defined by the W12. We all know that the work is the force into distance, then we are writing it as here because it is moving from 1 to 2. That's why we are taking the integral from 1 to 2 F dot ds. Here we are seeing the particle is moving, and the d is the distance, F is the force. Then we define the kinetic energy related to that, which will be equal to T is equal to mv square by 2. Then we can derive it as W12 is equal to T2 minus T1. Then we can define the T for the kinetic energy for the two positions. Work done equal to the change in the kinetic energy, means change in kinetic energy define the work done. Kinetic energy from the particle moving from 1 to 2, there will be a change in the kinetic energy, and that will be defined by the W12 is equal to T2 minus T1. Kinetic energy for the position 1 and kinetic energy for the position 2. Now conservative force. What are the conservative force? Here we define by the diagram. Here we see that in this diagram we are having the two system. If W12 is the same for any possible path from 1 to 2, the force is conservative. From 1 to 2, any possible path follows, then we can say F is conserved. W12 depends only on the end point, not on the path. If it is going from 1 to 2, then all are conserved. It means work function depend upon the points, depend upon the end points, not upon the path which is followed by. Here we are seeing that 3 paths has been defined. One is going from here to here, second is here, third is here. But if we define the conservation, that any path can be followed, but the end point is the 2. Equivalently, if we make the closed loop, means the particle, it means the work function for the 1 to 2 and 2 to 1, then the total work done is 0, and that will be defined by FDS, work done, total work done, is equal to the here we are seeing that the path from 1 to 2 and path from 2 to 1, FDS plus 2 to 1 FDS, which is equal to 0. Now work function will be 0 if we consider the loop. Potential energy. Potential energy, what are the potential energy terms? Where here we define the F is conservative, then F is expressed by F is equal to minus del VR. V is the potential energy that will define with respect to the R position of the particle, where V is the potential energy, and we are taking the derivative of that. Now work function is then expressed by W12 is equal to 1 to 2. Particle is moving from 1 to 2. We are not considering the closed loop, but we are taking the path of the particle from 1 to 2. Starting point is 1 and ending point is the 2. Then the work function is 1 to 2 FDS is equal to V1 minus V2. Here we take the del V, take the two position, one potential for the one position and potential energy for the second position, which is equal to the T2 minus T1, that is the kinetic energy. Then we can take the, because we know that W12 is equal to, in the previous equation we will define it as W12 is equal to T2 minus T1. Now here we are having the W2 is equal to V1 minus V2, then we can write it as T1 plus V1 is equal to T2 plus V2. It means for the position 1, the kinetic energy and the potential energy is T1 plus V1, and for the system it equal to the T2 plus V2. All are equal. Kinetic energy, total energy is equal for the one position and for the second position. If the force is conservative, the total energy T plus V is conserved. If we are having a question related to that, the total energy is, when the total energy will be conserved, then we will say if the force is conserved, then the total energy will be conserved. Total energy means potential energy plus the kinetic energy. This is the energy conservation theorem. This is very important. F is conservative, then the total energy is also conserved. Now, up to now we have discussed the single particle. Now a multiple particle system and its constraints we will discuss. Single particles, multi-particle system we will define. We define the force between the particles and then law of action and reaction of the particles. That is the Newton's third law. And we introduce the constraints, which is holonomic and non-holonomic constraints I defined, and then we discuss about the induced Lagrangian equation for this multi-particle system. System of a particle will be defined by for the more than one particle. Up to now we are discussing how F is equal to P. We are talking about the single particle. Now we are having the more than one particle. Then how we will define it as? Then we add the indices. Here you see that Fi is equal to Pi. Indices is added on both the side. Force for the multiple particles and the momentum for the multiple particles dot. Fi is equal to Pi dot, Ni is equal to Li dot. The previous equation we are using, force is equal to momentum, and here torque is equal to angular momentum. This is the linear momentum, this is the angular momentum, but this is for the multiple particles or the more than one particles. Now F may be working between the particles, then distinction between the internal and the external forces. Now the forces will be Fi, this is the force acting on the particle. It will be equal to summation of J Fji plus Fi per E. It means Fie, which define the force from outside. External force will be applied, and here Fji will define by the force from the particle J to the particle I. All the J particles will exert a force on a particle I. That's why we are taking the summation. Then the force acting on a particle I, we will take it as summation of J. J is the particles which exerts a force on the particle I, plus we add the external force which is applied to the system. That's why we define the force Fi is equal to summation of J Fji plus Fie. Now add up over the I to see the overall picture here. Now sum of the particles, you will define it as here. We see that summation I, we are taking all the J particle which exert the force on the I particles. We are having all the I particles, then we can write it as summation force on all the particles, I particles. That's why we are writing it as sum of the particles. That will be the summation I Fi is equal to summation I J. I is not equal to J Fji. Here we are taking all the I and J, but number I is not equal to J. The number of the particles I are not equal. Plus summation of I Fie, which is equal to we will take all the summation. That means we are here defining the external force which is acting upon all the ith particles. Here we are taking that the jth particle exert a force on all the ith particles. That's why we are taking all the force acting upon the ith particles of the system. Now we can take summation I must be less than J. That's why Fji plus Fji plus Fij, that we can write it as plus summation I Fie. This terms vanishes if Fij is equal to Fji. This we can write it as, because we are saying that I is not equal to J. That's why I must be less than J. This equation will be turned into Fji plus Fij plus summation of I Fie. If Fji is equal to minus Ji, then we can cancel this equation. Then the equation will become I Fi is equal to summation of I Fie is equal to 0. It means all the force acting upon it by the external agency, and this is a weak law of action and reaction. The forces two particles exert on each other are equal and opposite, where the two particle exert on force on each other will cancel each other. That's why it will become the 0. The CF of the strong law of action and reaction, which deals with the forces two particles exert on each other are equal, opposite, and along the line joining the particle. That will define the strong law of action. But here if it is equal, opposite, the two particles, then we can define it as a weak law. To explain it for the strong law, we define with the line joining the particle. The exert on each other are equal, opposite, and along the line joining the particles. Now sum of the particle here we will define. Now consider the equation of motion, summation I Fi, and it will be the summation I Fi E is equal to summation I Pi dot, we put Fi, we know that Fi is equal to Pi dot, then force is equal to linear momentum is equal to d square by dt, and then we can write it as P is equal to summation of MIRI, we can write it as. Now define the center of mass, we can write it as R is equal to summation MIRI divided by the summation MI. Mass of all the ith particles and its position divided by mass of all the ith particles. That's why we can write it as summation MIRI divided by M. Now the center of mass will be defined by MR double dot, which is equal to the summation of I Fi by E is equal to Fe. The center of mass moves like a particle of mass m under the total external force. The center of mass moves like a particle of mass m, the total mass of the body, under the external force which is applied, which is Fie. That is the center of mass. Mr double dot is equal to summation I Fie is equal to Fe. The total linear momentum, in this case when we are talking about the multiple particles or the multiple system, the sum of the linear momentum is defined as P is equal to summation I Pi. This is for the more than one particle. P is equal to summation I Pi. We are taking the momentum of all the particles that we define by the capital P is equal to summation I. P is equal to MRI dot. That's why here we are writing the MIRI dot, which is equal to MR dot. Taking the time derivative, then we can write it as P dot dp by dt. Here we are taking, that's why we are putting the dot here. It will be, we're not writing the dp by dt, but we are taking the time derivative. That's why we're writing the P dot, which is equal to MR double dot. If it is dp by dt, it will be d square r by dt square. That's why we are writing it as the r double dot, which is equal to Fe. Newton's equation of motion for the center of mass in the multiple particle system. Conservation of the total linear momentum. If the total external force is 0, then the total linear momentum will be conserved, because it is dp by dt is equal to 0, then P will be the constant. That's why P will be the linear momentum and it will be caused as a conserved. Assume the weak law of the action or reaction. The total angular momentum in the n particle system, then the sum of the angular momentum we will define. Similarly, we can define it for the ith particle. Then L will be replaced by the summation of I, angular momentum of all the particles here we are taking, which is equal to summation of I. We know that L is equal to R cross P. Here we write it as the Ri into Ri cross Pi, summation of I for whole the system. Then time derivative, and then we can write it as dpi is equal to Fi is equal to summation jfji plus may Fie. We can take the time derivative, dl by dt. We can write it as here summation, again I and j, I is not equal to j, into fji plus summation of r into Fip. Here what we do, that we are putting the value of Pi from this equation in this equation. Then we can explain the angular momentum, and this defined the total external torque. Why it is external? Because here we are having the external force Fi. Again, these terms can be vanishes if Fj I satisfied the strong law of action or reaction. Then angular momentum will be the function of the total external torque. The total angular momentum, we are considering the strong law of action and reaction, and then we define it as dl by dt, or we can write it as L dot, which is equal to r position into the external force and for all the I particles, and then we define it as force into the position, then it will be the torque, then summation I and IE external torque, which is equal to, we can write it as NE. This is the conservation of the total angular momentum. If the total angular momentum, how we define the total angular momentum is conserved? If the external torque is 0, it means NE will be 0, then dl by dt will be the 0, then L will be the constant, and then we can say it is conserved. The total angular momentum L is conserved. A multi-particle system is equal to extended object can be treated as if it were a single particle if the internal force obey the strong law of action and reaction. The multiple particle system, or we can say extended object, can be treated as if were the single particle if the internal force obeys a strong law of action and reaction. What are the laws of action and reaction? Here we see that F12 is equal to 0, Q plus V1. The most of the forces we know obey the strong law of action and reaction. What are the examples? Which are the gravity and the electrostatic force are the strong law of action and reaction. There are the rare exceptions, means Lorentz force felt by moving charges, conservation of linear and angular momentum, then taking the electromagnetic field, the particle exchange forces with the field itself has a linear and angular momentum, and then conservation law is stored in this action and reaction. What are the conservation laws? Conservation laws defined by the weak law of action and reaction and the strong law of action and reaction. In the weak law of action and reaction, the linear momentum is conserved. In the strong law of action and reaction, angular momentum is conserved. Now PLN must be conserved if the law of physics are isotropic in space. No spatial origin will define, no spatial orientation will define. Then we accept these symmetries as a fundamental principles. All the forces must satisfy the action and reaction and obeys the Newton's third law. Either it will be the weak or it will be the strong action and reaction. The total angular momentum, define the particle ith position from the center of mass, then we define it as Ri dash is equal to Ri minus R. Then we will define the velocity, Vi is equal to Ri dash, Vi dash is equal to Ii dash, or we can write it as V is equal to R. Then we calculate the total angular momentum in terms of the position of the particle in the center of mass. Then L is equal to summation Ri into Pi, which is equal to summation I. We put the value of R here, which is equal to R dash plus R. Now we take this R that side. Now Ri will become Ri dash plus R into, we put the value of Pi Mi into Vi dash plus V. Then L is equal to R into mv plus summation of I Ri dash into mi vi. After solving this, we are getting the angular momentum, total angular momentum. So total angular momentum L is equal to the angular momentum of the motion concentrated by the center of mass. This is defined the center of mass and the angular momentum of the motion around the center of mass. Here we define the two part for the total angular momentum. One, we define the angular momentum of the motion concentrated at the center of mass, and the second one is the angular momentum of the motion around the center of mass. This will define the total angular momentum. One is concentrated on the center and one is around the center. The kinetic energy for the system, for the ith system, we define the total work function, where we define W12 is equal to summation I12 to Fi dSi. We are taking from the previous equation. There we define the F dot ds. Here we define the work function for 1, 2 for all the ith particles. The position 1 and 2 are now configurations. We set the position 1 and 2. Now use the equation from the motion from the previous derivation. We know that W12 is equal to T2 minus T1. Now we can write it at T is equal to summation of I 1 by 2 mi vi square, kinetic energy for the ith particle, that will define by T, total kinetic energy for the particles. Now we can split this T into two pieces. One is that T is equal to summation of 1 by 2 mi v plus v dash into v plus vi dash. This v square is split into two parts, and we can write it as 1 by 2 mv square, and we write it as plus summation of I 1 by 2 mi vi square. It means the total kinetic energy is equal to, for the ith particles, will be defined as motion concentrated at the center of mass, and again the motion around the center of mass. That will define the kinetic energy. In the previous we also defined the total angular momentum concentrated around the center of mass. First is concentrated at the center of mass and around the center of mass. Similarly here, at the center of mass and around the center of mass, the kinetic energy. Potential energy, we define it as we use the conservative external forces. Fi is equal to minus summation r del I vi. That time we defined what F is equal to del V minus del V, del for the single, now here for the ith. Summation I 1 to 2 Fie dot dSi, we can write it as minus. This force can be defined in terms of the potential energy. Then we can write minus del I Vi in place of the Fe for the particle moving from the 1 to 2. Now it will become the summation of summation I Vi 1 to 2. Assume also conservative internal forces. It will be the Fji. Internal forces means J is exerting a force on the I. Then we can write it as minus del I Vij. Potential will becomes when the internal jth particle exert a force on the ith particle. To satisfy the strong law of the action reaction, we can write Vij is equal to Vij Ri minus Ia. It means potential depends only on the distance. Here we see that position, distance. These R and R the distances. Then now this equation, which is summation of Ij 1 to 2 Fji dot dSi is equal to minus summation of Ij, I is not equal to 0, j 1 to 2 del I Vij dot ds. Simply we put this value here. Now we solve it as, and we finally we have 1 by 2 summation Ij, I is not equal to j, Vj 1 to 2, and here we know that del I is the gradient, del by del xi, del by del yi, del by del zi, means we are considering the position of the particle in the 3 dimensions in x, y, z direction of all the ith system. Energy conservation, for that, for all the forces are conservative, then we can define the total potential energy will be V is equal to summation of Ii plus 1 by 2 summation of Ij. I is not equal to j, Vij. Similarly here the total energy T plus V is conserved. Previously we have defined that T is conserved, now we have V is also conserved. The second term is the internal potential energy. This is the internal potential energy, and it depends on the distance between all the pairs of the particles. And constants if the particles' relative configurations is fixed, that are the example of the rigid body. Thank you very much.
With this note, thank you so much for giving us this session on classical mechanics. Dear friends, there is not more for you in this series, and in the forthcoming sessions we are going to discuss more. You are just requested to be with us, connected to us, and if you wish to ask a question pertaining to this topic, then feel free to write to us at info.cec@nic.in. We are taking your leave with the promise that very soon we are going to meet and discuss more. Till then, keep watching us. Thank you for watching CEC Gurukul Live Lectures. Thank you, ma'am. Thank you once again.
Thank you.